I played Hollow Knight Silksong, and even though I'm just a few hours in, I think the movement feels really solid. And that got me thinking, how would I approach writing a carrot controller like this? And that is what we'll be doing today. Don't worry, no spoilers here, we'll solely focus on the movement of the Hornet. At the end of this two-part series, you will have a fully functional carrot controller, including animations, programmed in such a way that you can easily build upon it. In this video, we focus on moves like walking, jumping, double jumping, falling, floating, ledge climbing, and ledge jumping. And in the next video, we add more special moves to it, like wall sliding, wall jumping, wall climbing, and dashing into sprinting. As usual, the project files will be available on itch, which you can find by following the link in the description. And without further ado, let's get into it. Project setup. First of all, the project files on itch contain a template that you can use to follow along with this tutorial. Just download the tutorial ready templates.zip file from itch and copy the assets folder to your own project. The project setup contains a small test level with a player controller. The controller currently features basic components including a character body 2D node as the root, a collision shape, and a camera that follows the player. Note that I have a capsule shape as the collision shape, which has a radius of 9 pixels and a height of 48 pixels, which is ideal for a pixel art character. You can also use a rectangle shape instead of a capsule shape. And then we have an animated sprite node with various animations that we'll use throughout the script. Keybinds. Before we start programming, we need some keybinds. Go to project settings, select input map, and add the input actions move left, move right, jump, and sprint. For moving left and right, I'll bind A and D. For jumping, I'll bind space, and for sprinting, I'll bind shift. You can bind the keys however you prefer. You can also bind a joystick to moving left and right. I will take this into account when writing the script. State machine. With our player controller script open, we will start programming. Right now, I start with a fairly empty script, which only contains the physics process loop that calls the move and slide function. We start by creating a state machine. A state machine can be seen as a sort of flowchart of all the states that our player can be in. Future Me has made a video about them, which you can watch by clicking the link in the description, and if it's not there, you can keep bothering me in the comment section until it is. Create an enum called state and define all the state names inside. For this video, those states will be the fall state, the floor state, the jump state, the double jump state, the float state, the ledge climb state, and the ledge jump state. Below that, we'll define a variable called active state and assign it the value state.fall to be the start state. Next, we create a function, process state, that takes delta as a parameter and in the physics process loop, call it before the move and slide function. Inside the process state function, we use a match statement on our active state variable and for now, only match it against the fall state as that's the one we start with. This is where we will define player movement and state transitions. Then we write another function called switch state, which takes toState as a parameter and inside assign toState to active state. Again, we write a match statement on our active state variable and match it against the fall state. This is where we can set state-specific things that only need to run once on entering the new active state. Lastly, in the ready function, we want to call this switch state function using the active state as a parameter. This may seem redundant, but it will help us properly initialize the start state, whatever that start state may be. And with that, our simple state machine is already in place. Now we can go to the next phase, which is writing the states. The fall state. Our programming journey starts with Tiny Mac's stick figure over here. Tiny Mac's stick figure is good at, well, nothing really. He's a lazy bum who ignores the laws of physics by floating around all day. So let's change that. We'll start by making him experience gravity. Let's start by looking at falling in Silksong. When the Hornet starts falling, her fall speed quickly increases over time until she reaches a certain threshold at which she falls at a constant speed. While she's falling, she's able to move horizontally toward a given input direction. To prepare for writing our first state, we should start by adding our animated sprite node to our script so we can play animations and flip the sprite. In case you're using a normal sprite node, add that instead and skip the animation code. Right-click our sprite node and enable access as unique name. and drop it into the script whilst holding down Control. We also need a few constants. First, we have the fall gravity constant, which will receive a value of 1500.0. Second, we have the fall velocity with a value of 500.0, and third, walk velocity with a value of 200.0. Note that if you have a bigger character controller than the one used in this video, you will likely want to use higher values. In the switch state function, we should define what happens upon switching to the fall state. Currently, the only thing we want to do is play our fall animation. Since we should be able to move around while falling, let's write a new function at the bottom of our script called handle movement. In it, we first want to receive the input values from our left and right movement keys and store them into a local variable called input direction. Notice that I encapsulate the input inside a scinev function call, which turns negative values into -1.0 and positive values into 1.0. This way, joystick users will walk at full speed, even if they don't fully tilt their joystick to the left or right. Then we check if input direction contains a value that is not 0. When true, we flip the sprite when input direction is smaller than 0. We can now set the x velocity by multiplying the input direction by the walk velocity constant. In the process state function, since we call this function every physics frame, we can define player movement and state transitions based on user input. First, while falling, we want to increase our y velocity using a simple move toward function. In there, we move the y velocity towards the fall velocity by the amount fall gravity times delta. We multiply by delta here so that the movement becomes time dependent. Then call the handle movement function to allow our player to move horizontally while falling. Let's test to see if Tinymac's stick figure plummets to the ground. Right now he should fall and we should be able to move him around. The floor state. When the Hornet is on the floor, we can stand still, move to the left or move to the right. Nothing too exciting yet. Right now, all we need to do is define what happens when the floor state is active in the process state function. First, we want to play our walk animation when the player gives an input, and if not, we play the idle animation. We should be able to move horizontally during the floor state, and we can now simply achieve this by calling the handle movement function we created earlier. Let's add our first transition. To prevent our player from walking in the air, we need to make sure that if we are no longer on the floor, we switch to the fall state. Then in the fall state above, let's make sure to do the opposite and switch to the floor state when we land on the floor. When we run the scene now, upon landing on the floor, Tinymac's stick figure should be able to stand still while playing the idle animation. And if we give any movement input, he should be able to move to the left and to the right while playing the walk animation. When moving over an edge, he should start falling again. Okay, cool. Tinymac's stick figure can fall and walk. But now he's stuck. There's no way back up there again, which brings us to the jump state. In both the first Hollow Knight and Silksong, the jump behavior depends on how long you are holding down the jump button. When you press and hold the button, the player performs a full jump. When you release the button in the middle of the jump, you'll come to a full stop and start falling immediately. The jump also includes a coyote time, which is a small grace period in which the player is allowed to jump after walking off an edge. In preparation for our jump state, we need to add a timer node to our player, which we call coyote timer. Set the timer to update during the physics loop, set a small cooldown, and enable one shot. Then add it to the script. In the script, add the constant jump velocity, which I give a value of -600.0, and the constant jump deceleration, which I give a value of 1500.0. In our switch state function, let's determine what should happen upon entering the jump state. Here we want to start our jump animation, set the y velocity to the jump velocity constant, and stop our coyote timer. Then we also need a place to start our coyote timer. At the top of our switch state function, before setting our active state, add a new variable, previous state, and assign it the value of active state. Then upon entering the fall state, we can check if the previous state was the floor state. And if true, we start the coyote timer. Below, we should also handle the jump state in our process state function. Start by decelerating the y velocity towards 0, using the jump deceleration multiplied by delta as step. Since we should also be able to move around during the jump, we can simply call the handle movement function. Upon releasing the jump button, or when the y velocity is or becomes bigger than 0, we should set the y velocity to 0 and transition to the fall state. Both the fall state and floor state can now transition to the jump state. Up, where we handle the fall state, when we press the jump button while the coyote timer is running, we transition to the jump state. Note that I'm using an elif statement for this. Then, in the floor state below, we can simply transition to the jump state when the jump button is pressed. Upon running the game, Dynamic Stick Figure should now be able to jump out of this gap. But he's still stuck. The jump is not high enough to reach the top of the next wall. Which brings us to the double jump state. When you receive the fade down cloak in Silksong, the Hornet can reach new heights by performing a double jump. Upon being airborne, pressing down the jump button allows the player to perform a double jump which resets upon landing. To prepare for the double jump, all we need is a new constant and a new variable. The constant will be double jump velocity with a value of negative 450.0 and the variable will be can double jump with a value of false. Upon entering the double jump state, we play our double jump animation, set the y velocity to the double jump velocity constant we just created, and toggle the can double jump to false. To prevent cancelling out our double jump animation upon entering the fall state, we should add a condition to it that only plays the normal fall animation if the previous state was not double jump state. After using the double jump, it should reset upon landing, so let's add the floor state as a condition. For consistency, we should put it between the fall and jump states. And in there, we need to set can double jump back to true. Apart from the start velocity and animation, double jumping behaves the same as normal jumping. So instead of writing a whole new state to handle the double jump, we can simply add it as a condition next to the normal jump state. We can only transition to the double jump state when airborne. In our fall state, since we need the jump button for both the coyote time jump and the double jump, move the coyote time check inside the jump button check, and below that we add the double jump check using an elif statement, and upon true, the transition to the double jump state. With his newfound ability to jump twice, Dynamic Stick Figure should now be able to jump on top of this wall. So, what's next? Let's give him some motivation and tell him that there's a cake on top of this ledge. But even with the double jump, it's impossible to reach, which is why we will need to learn how to float. The float state. Once you receive the Drifter's Cloak in Silksong, pressing and holding down the jump button while falling causes the Hornet to start floating instead. That is until you release the jump button, causing the Hornet to begin falling again and starting a small cooldown until you can float again. We need to prepare a few things before we can start floating. We need to add a timer node to our player, which we call float cooldown. Make sure the timer updates during the physics loop, has a small cooldown, and that one shot is enabled. Then add it to the script. Add a new constant, float gravity, with a value of 200.0, and the constant float velocity with a value of 100.0. Upon entering the float state, we first check if floating is on cooldown, and if it is, we simply set the active state back to the previous state. If it's not on cooldown, we want to play the float animation and set our y velocity to 0. The float state will look very similar to the fall state. So upon handling the float state, we can just copy and paste most of the fall state and replace the fall constants with the float ones. To stop floating, we need to add a transition back to the fall state when the jump button is no longer pressed. Here we should also start the cooldown timer. The only transition to the float state we need is from the fall state. Since we use the same button for both double jumping and floating, all we need to add is an else statement to the coyote timer and double jump checks, and then switch to the float state. Let's check up on Dynamic Stick Figure again. If it all went well, we should be able to make him jump, then double jump, and then float. Let's see if he's able to jump the gap. But even though he tries his best, flapping his arms and stuff, he still can't make it. If only there was somehow a way to hold on to that ledge. The ledge climb state. What was really unique to the moveset of the Hornet in comparison to the Knight is the ability to grab onto a ledge and climb on top of it. Let's look exactly at what happens. First, when you fall or float into a ledge while holding down input towards that ledge, the Hornet grabs it and automatically climbs on top of it. If you are not holding down input towards the ledge, you will just fall past it. During her climb animation, we cannot move her to the left or right. However, we can perform a jump cancel, which allows us to exit the animation early. You can jump cancel anytime during the animation, and the further you jump cancel into the animation, the further you'll jump on the edge. And lastly, ledge climbing resets our ability to perform a double jump. To prepare for ledge climbing, we need to set up several things. Let's first go to our player scene, and in there let's add a raycast node, which we call ledge climb raycast. We will use it for detecting ledges. Place the raycast somewhere above the player and point it diagonally in front of the player. Let's add another raycast and rename it to ledge space raycast, and then place it next to our player. We will use this raycast to detect if there is enough space for the player to fit on top of the ledge. To ensure enough space, point the ray upward and make it a tiny bit taller than the collider. Back in our script, select the player collider, the ledge climb raycast and the ledge space raycast. Enable accessible as unique name for all of them and then drop them into the script. Let's add one more variable called facing direction and assign it 1.0. To finish our preparation, in the ready function, we add our player as a collision exception to the ledge climb raycast to prevent it from detecting our own collision shape. Upon entering the ledge climb state, we want to play the ledge climb animation and set our velocity to 0. We should align our player's Y position with the ledge, and we can do so by assigning it the ledge climb raycast its collision point Y position, and set can double jump to true. Let's scroll to the bottom of our script and make a change to our handle movement function. Inside the if statement, let's assign input direction to the facing direction. To flip the raycast into the right direction, take its X position and assign it the input direction multiplied by the absolute value of itself. Then do the same for the target position. Lastly, we force update the raycast to prevent retrieving outdated collision information. Then we should add 4 new functions to the bottom of our script. First, the isInput_toward_facing function. In this function, compare the sign of our movement input to the current facing direction. We use this function to prevent grabbing onto a ledge when no input towards it is given. Then, the isLedge function. In this function, we compare multiple conditions to check if a ledge is valid. The conditions are as follows. Is on wall only has to be true. Our ledge climb raycast has to collide with something, and that something that our raycast is colliding with has to have a surface pointing upward. We can simply check this by comparing the collision normal with the up vector. Next, we'll add the isSpace function, which we use to check if there is enough space to fit our player on top of the ledge. We should always call this function after the isLedge function. First, we reposition the ledge space raycast to the collision point of the ledge climb raycast. Then we force update the ledge space raycast since we just moved it, and then we should return true when the ledge space raycast is not colliding. Our fourth and last function we will call ledge climb offset. We will use this function to perfectly snap our player to the top of the ledge. This function returns a vector 2 composed of the size of our collision shape. Assuming the collision shape of our player is a capsule, the x value will be the capsule its radius multiplied by 2, and the y value will be a negative value of its height multiplied by 0.5. If the shape of your player is a rectangle, you can use the following instead. Let's add our ledge climb state to the cascade of states inside our process state function. Inside it, we should write an if statement that checks if the animation is not playing, because we only have to act once the ledge climb animation is finished. Once it is finished, play the idle animation instead. Then we create a new local variable called offset, assign it the ledge climb offset function we've just created, multiply the x value of the offset by facing direction, and increment our position with it. and transition to the floor state. All that's left to do is add 2 transitions to our ledge climb state. The first one in our fall state. In the new elif statement, check if the input is towards the facing direction, if we detect a valid ledge, and if there is enough space for the player to fit. And if all conditions are true, transition to the ledge climb state. We can just go ahead and copy the whole elif statement plus transition and paste it at the bottom of our float statement. And with all the effort we went through, our player should now be able to grab and climb onto a ledge. Let's test it out with TinyMac stick figure over here. So, with our previous attempt, we didn't make the jump, but with our newfound ability to climb ledges, he should now be able to make it. And would you look at that? TinyMac stick figure is now able to climb all the ledges he wants. But there's one last thing missing right now, and that is being able to jump cancel. Which brings us to the next state, the ledge jump state. In the overview of our ledge climb earlier, I mentioned that you can jump cancel the animation. The later you jump cancel, the further you land on the edge. For our preparation, we only need a single constant called ledge jump velocity, which we give a value of -500.0. Then upon entering the ledge jump state, we want to play an animation. Let's use the double jump animation because I think that looks funny. And we also set the Y velocity to the ledge jump velocity. Just like we did with the double jump state, in the process state function, we can simply add it as a condition next to the normal jump state. We only need a single transition from the ledge climb state to the ledge jump state. So, in the ledge climb state, we need an elif statement that checks if we just pressed the jump button. If so, we first create a local variable called progress, which we assign the inverse lerp of 0, the animation its total frame count, and the current frame. Progress determines how much of the animation has passed, with a value between 0 and 1. Now we can just copy and paste most stuff from the previous if statement, but instead of only multiplying the x value of the offset by facing direction, we also multiply it by progress. And instead of transitioning to the floor state, we transition to the ledge jump state. TinyMac stick figure should now be able to jump cancel his ledge climbs. And with that, we have a pretty decent character controller. In the next video, we'll add more special moves like wall sliding, wall jumping, wall climbing, sprinting, and dashing. That video will hopefully be released 1 week after this one. And if you enjoyed this video, please consider subscribing and ring the bell to don't miss out on any new videos. See you then!